All right. So we will continue our discussion on of second order differential equations and complete the discussion on homogeneous second order differential equations and move on to say a few words about inhomogeneous stuff. Okay. So we did a bit of stuff in the last lecture. We basically showed two things. So what I will do is I'll start with these two things in a very brief fashion, even if you don't go through all the proof and things like that. So a brief recap of what we did last class. The content of last class was basically two important statements. The first important statement was the existence of solution of a homogeneous differential equation. So you had something like y double prime plus p of x y prime plus q of x y equal to 0, right? So this is a general linear second order homogeneous differential equation, ordinary differential equation. And we claimed that if these functions p of x and q of x, p of x, q of x, continuous on some interval I, this basically implied that suppose if I also supplant this with an initial value of y at x0 equals some k0 and y prime at x0 equals k1. Okay, so this is a second order differential equation. So I need two constants of integration. If I have a third order, I need three, and so on and so forth. Basically, if these functions p of x and q of x are continuous, it means that a unique solution exists. So in some sense, this is even simpler than our discussion of first order, where you actually needed two different conditions for guaranteeing uniqueness. In this case, all you have to do is make sure that both these guys are continuous. Unique solutions exists on I. Okay, I'm also assuming that the point x0, where the initial condition is specified, is in this interval. Okay. So let's look at a quick example. So suppose I have an equation like 2y double prime plus, I don't know, 3x square over x square minus 2y prime plus 8 over xy equal to 0, something like this, right? So my p of x is this guy and my q of x is this guy. So now I have to understand if these functions are well behaved or they have some points at which they are not well behaved. And you can easily see that there are points at which these functions blow up, right? So these points typically, these points in this example are x equals plus minus root 2 and x equals 0. So certainly at these points, there is something iffy going on and the continuity is certainly not guaranteed. So now I will supplant this with some kind of an initial value. So let us say that my initial value, so I'll call this example 1. My initial value is something like y at 0 equals 1 and y prime at 0 equals, I don't know, minus 1. So the question is, does this have a unique solution? Can you take a guess? So first, let us find if there is any interval in which this function is well behaved. Well, of course, I can choose any interval like, I don't know, square root of 2 and infinity, right? In the interval square root of 2 and infinity, remember that when I put an open bracket like this, the point here is not included, right? So this is an open interval. The square root of 2 is not included. So obviously this p of x and q of x are all very continuous in this interval. But the point is this interval doesn't encapsulate the point at which the initial condition is given to me, which is y equal to 0. At y equal to 0, there is no escape. I cannot find an interval where I encapsulate the point at which the initial condition is given to me, and though an interval that is free from any sick behavior. Okay, so in this case, obviously, I have to conclude that since I cannot find an interval like that, a unique solution cannot possibly be determined. The answer is no. Okay. Again, please stop me if there is any question. Suppose if I have the same differential equation.
No solution or no unique solution?
Yes. So what we will do is later when we actually solve these guys, maybe I'll solve the exact same example and find out why, and it'll actually be transparent what this means.
Okay.
Yes. So there is no unique solution. In fact, it's very hard to see how a solution can exist, right? Where at the point where the functions blow up, the differential equation itself is not has a singular point at the point x is equal to 0. Now, suppose if I change this slightly and say that y of 3 equals 1, this is your initial conditions, and y prime at, I don't know, 2 equals 5. Okay. And now can you think of some interval in which you can claim that a unique solution exists? Well, you simply have to make sure that the points at which your initial values are specified are contained in this interval. So I have to make sure that the point x is equal to 2 and x is equal to 3 are in this interval. And I would have to make sure that this interval is free from any point at which the functions blow up. So in this case, of course, I can safely take square root of 2 and go all the way to infinity. There is absolutely nothing wrong. Okay. So there is a question. So we don't have any methods to determine the existence of solution here. Well, so this is existence and uniqueness rolled together. So whenever I claim that whether a unique solution exists, that presupposes that a solution does exist, right? So the converse is not true. Just because a solution exists doesn't mean it is unique. But when I claim that there is a unique solution, it obviously means that I know that at least one solution exists, and I'd have to understand if the solution is unique. So when I say that a unique solution does not exist, it means that there is no one solution. Now the question is, does it mean that there is no solution? Well, that we will answer as we go along. That's what I answered in the beginning. It's much better to actually solve this differential equation and try to understand that question. Okay. So to understand, let us try to solve it at some point and figure out y of x and see if it has any sick behavior at some point. So I should also warn you that we have said quite a bit about second order differential equations, and we will talk more today. But the only solution that we have done is one for constant coefficients. So we have not actually learned how to solve equations of this kind, right? Where p of x and q of x are functions of x. So we'll certainly do that. As a second example, consider y double prime. I will look at a slightly simpler example, 1 over x square minus 1 y prime plus y equals 0. Okay. So obviously this is ill-behaved at x equals plus minus 1. So suppose if I give you my initial conditions as y at the point 0 equals 1 and y prime at the point 0 equals 4, say. Okay. Now can you figure out some place where a unique solution exists? In this case, you would actually find that this theorem is actually quite powerful. It narrows down the region quite a bit. For example, now again, I have to apply the same considerations. I'll have to include the point x is equal to 0 because that's the point where the initial conditions are given to me. And I would have to make sure that I exclude the points where the function is ill-behaved. So I'll have to certainly exclude the point +1 and -1, and I'll have to include the point 0, which means the only interval that is available to me is -1 to +1. This excludes the two endpoints and includes 0. So in this interval, a unique solution exists. Okay. So this is what the theorem really means. So how do you, given a differential equation, how do you figure out the uniqueness of a solution in some open interval? Excuse me. Okay. And the second thing that we discussed last lecture was the idea of a Wronskian. Okay. What was a Wronskian? So given two solutions of a differential equation, the second order differential equation, the goal is to try and understand if these guys are linearly independent or not. And to do that, you form this particular linear combination y1, y2, which is y1, y2 prime minus y2, y1 prime. And then basically check if this guy is 0 or not. If this guy is 0, then by simple separation of variables and integration, I can figure out y2 as a simple multiple of y1. So these guys are not linearly independent. So W not equal to 0 implies linear independence. If W is equal to 0, then the two solutions are linearly independent. So you'll have to keep looking for a second solution that is linearly independent. Okay. So we will talk about why we need to look for a second solution that is linearly independent in just 1 second. But I want to say a few words about the Wronskian, because you might actually think that we are making a big deal out of this. Actually, it turns out quite remarkably that given a differential equation, I know what the Wronskian is, even if I don't know what the solution is. Okay. Now, this is actually a very bizarre thing to say, because Wronskian, at least the way we have defined it up till now, explicitly depends on the solutions, right? So given you have found two solutions, y1 and y2, you form this particular combination, take the derivatives and subtract and all those things. And this is what gives you the Wronskian. But there is a very nice formula called the Abel formula that tells you that given a differential equation, there is a very straightforward way to understand what the Wronskian is. So I'll say a few words about this, and this will tell you why W not equal to 0 is very interesting. So let us start with this particular formula that we have. Okay, W, the way we have defined is y1, y2 prime minus y2, y1 prime. And where y1 and y2 are solutions of the homogeneous differential equation, y double prime plus p of x y prime plus q of x y equals 0. Okay. So now the goal is to try and figure out a formula for W regardless of y1 and y2. So to do that, first go ahead and differentiate this expression with respect to y. So W prime, which is dw dx, is given by y1 prime, y2 prime, plus y1, y2 double prime. That's the differentiation of the first term, minus y2 prime, y1 prime, minus y2, y1 double prime. Okay. And you find that this and this cancel, which leaves you with W prime equals y1, y2 double prime minus y2, y1 double prime. And you also know that y1 and y2 are solutions of the differential equation. So I can simply substitute what is y2 double prime and what is y1 double prime. So remember that y2 double prime plus p of x y2 prime plus q of x y2 will have to be equal to 0 if y2 is a solution, and similarly for y1, which tells me that I can trade the second derivative for a linear combination of the first derivative and the function itself. So this is basically minus p of x y2 prime minus q of x y2. So substitute this, W prime equals, and so far it seems bizarre because everything still depends on y2 prime and y1 prime, but things will clean up very fast, as you will see. So y1 times y2 double prime is minus p of x y2 prime minus q of x y2 minus y2 times, similarly, y1 double prime would be minus p of x y1 prime minus q of x y1. Okay. And here's the point. This and this would neatly cancel. Okay, as you can easily verify. There is a minus q of x y1 y2 in the first term and a plus q of x y2 y1 in the second term. And even now, it doesn't seem like a very useful formula because it still has y1 and y2. But now I can take p of x out common. In fact, I'll take minus p of x out common. And what remains on the right-hand side is basically y1, y2 prime minus y2, y1 prime, which, as you recognize, is basically the definition of the Wronskian. So the W prime is simply, okay, So it turns out that even though I don't know what the solutions y1 and y2 are, I can actually write down a very simple first order differential equation for the Wronskian, assuming that y1 and y2 are indeed solutions. Okay. So you can go ahead and integrate this very simply. So dw over w equals minus p of x dx. Remember that p of x is known to you because you know what the differential equation is, right? So it doesn't depend on q, it only depends on p. So logarithm w equals minus integral p of x dx plus some constant. I'll integrate from some x0 to x because I'm looking at some interval where I want the where the solutions exist. And if I want to figure out what this constant is, so I can call this constant some log of a and evaluate this at x is equal to x0. Okay. At x is equal to x0, w would be y1 of x0, comma y2 of x0. And let us say that this w is known, it is given to you. After all, it's a first order differential equation, so I should give you something. I don't give you w at any value, but I simply say that w at x is equal to 5.5 is 2 or something like that. So this is known to you. Okay, let's call this with an abuse of notation. I'll call this w of x0. Okay, but the x0 dependence comes through y1 and y2. So plugging everything together, you actually find that the Wronskian is basically, excuse me, again, I'll write it as w of x, but what I mean is w, which is a function of y1 and y2. And the y1 and y2 are functions of x. Exponential minus integral x0 to x p of x dx. Okay. Now, as long as p of x is a well-behaved function, this exponential integral p of x dx is never going to either blow up or be zero, right? So if w of x0 is not equal to 0, I'm guaranteed that w of x is also not equal to 0. So this was the same thing that we proved, I think, in a slightly more laborious fashion yesterday. But the Abel formula gives you a nice way of seeing things. Okay. So this is why Wronskian is actually quite a very interesting and a powerful method, because even if you don't know the solutions, you still know something about how the solutions should behave. Okay. So this is a useful thing to know. Sometimes if you're asked to compute Wronskians, you can simply look at the differential equation and do a very simple integration and figure it out. Okay, so this is basically the content of the first two theorems. The other two, I will simply state without actually proving it. I'll say a few words about it. The other thing that we have to worry about is, first we worried about the uniqueness of the initial value problem. But now I can look at the differential equation itself. So let me go ahead and write the Let me go ahead and write the differential equation again. P of x y prime plus q of x y equals 0. So suppose if I simply ask what is the general solution of this differential equation and does a general solution exist? So remember again that the general solution should be given by a linear superposition of the linearly independent solutions. And the answer to this is again the same answer as before. Your book calls this theorem 3. Basically, if p of x and q of x are continuous on an interval I, then let's call this equation 1. A general solution to equation 1 exists. Okay, so by way of showing whether a general solution exists or not, you have to basically do the same things we did for the examples that we just discussed. Okay. And we'll not go ahead and prove this in any detail. The proof is given in your textbook, so it's fairly simple. I invite you to go through it. And if you have any questions, you can always ask me. But what is more interesting is that suppose if you write down the general solution as y of x equals c1y1 plus c2y2, then this general solution includes all possible solutions. Okay, so this is again given as a theorem, but you don't have to view it as a theorem. It's actually a very straightforward thing to understand. So I will write down the statement: the general solution contains all possible solutions. The question is, what does this mean? Okay. So again, I invite you to think about the simple idea of vectors, right? So what does this have to do with vectors? Given I have nailed down my basis vectors, right? So suppose if I am given, let us say I live in a two-dimensional vector space, and I know that my basis vectors are I and j. Okay. Now, any vector in this basis space can be written as how much of the vector lies along the I direction and how much of the vector lies along the j direction. Okay. So any vector can be written as some amount of a along the I direction plus some amount of a along the j direction. Okay, so this is what a basis really means, as we have discussed before. So which means a general vector in this two-dimensional space can be written as a linear combination of the basis vectors. Okay, so I can trivially extend this to 3 dimensions and 4 dimensions and so on and so forth, as long as I know what the basis vectors are. The second point is, again, by an analogy with vector space, I and j need not be unique. For example, I can think of another set of basis vectors, as long as the basis vectors follow certain rules. In this case, the rules are I dot I should be 1 and I dot j should be 0. So I can form E1, E2, where E1, E2 is given by I plus j over root 2, and E2 is I minus j over root 2. And you can quickly verify that E1 and E2 also satisfy the same properties. E1 dot E2 would be 0, and E1 dot E1 would be 1, and E2 dot E2 would be 1. And I can write any general vector in this two-dimensional space, again, as a linear combination of E1 and E2, but the coefficients would be different. Okay. But notice that I can write this basis vector as a linear combination of those basis vectors. E1 can be written as a linear combination of I and j. E2 can be written as a linear combination of I and j. Now, which one is more basic than the other? Well, that is a very difficult question to answer, and you basically choose the set of basis vectors that makes your problem easier. Okay. Now, for example, in this case, my axis is like this, and in this case, I've basically tilted my axis, right? So that is what it means. Anyway, so that question really doesn't have a lot of meaning, and this is obvious to you, right? Because you know vectors very well. That there is nothing sacred about one set of basis vectors over the other, but given a set of basis vectors, you have to be consistent. So suppose if you decide that you're going to do E1, E2, then you should not keep going back and forth, because the coefficients of these vectors depend on the basis. Okay. So given a set of basis vectors, a vector has specific coefficients. If I change the basis, the vector has different coefficients. But the vector is a vector is a vector. So if you look at the vector as a line, directed line segment in space, that is just sitting there. So your choice of ij or E1, E2 simply is a difference between how you choose to describe this vector that is just sitting there, not doing anything. Okay. So this is the concept of a basis. So in that sense, the statement in differential equations that a general solution contains all possible solutions is exactly equivalent to this. So what I mean is the following. So suppose if I have two linearly independent solutions, let us say that I have solved this differential equation 1, and I give you two linearly independent solutions. Y1 and Y2 are linearly independent solutions. Okay. Now there is nothing more to determine. Just as in this case, when I know what I and j is, there is nothing left to understand about the space itself. Okay, so in this case, when I understand what the basis vectors are, I understand about the linear vector space in which I'm operating. So to throw out a few words. In this case, when I understand what y1 and y2 are, I understand the basis functions in this so-called function space, even though we will probably not use this language. So what it means is basically somebody else can come in and say that, oh, wait a second, I have figured out a solution for this differential equation. This solution is some y of x. And then you say that, well, can you prove that this is a solution? And this person plugs this y of x that he has found in this differential equation 1, and shows you that 0 equals 0. Everything is fine. So your job is to then tell him that, aha, but your y of x is nothing special. You see, I can always write your y of x as some c1 times my y1 plus some other c2 times y2. So this is what it means when somebody claims the general solution contains all possible solutions. It doesn't mean that one cannot write down a different solution, but the point is there is no big deal about this other solution, because I can always decompose this solution as a linear combination of my basis solutions. Okay, so any other solutions, every other solution that somebody can write down can be written as a linear combination of these solutions. So how do people figure out all these other solutions? They solve the differential equation. They solve the differential equation and find that your differential equation is solved by some y of x. And then you basically, kill all their joy by pointing out that, oh, this is nothing special. I can write this as a linear combination of my solutions. A corollary to this statement is that there are no singular solutions to a second order differential equation. There are no singular solutions for a second order ordinary differential equation. This was not true for first order, by the way, right? So the theory is a little more tight for second order differential equations. What are singular solutions? Singular solutions are those solutions that solve the differential equation but cannot be gotten from the differential equation by any proper methods, right? So you also solved a couple of tutorial problems that had a singular solution for a first order differential equation. By inspection, you could show that this function is a solution of the differential equation, though you had no means of figuring out from the solution of the differential equation itself. That is not true for a second order differential equation. Given a second order differential equation and given two linearly independent solutions, every other possible solutions is always expressible as a linear combination of these two. Okay. So for people who are wondering about this a little bit, please understand that you have already seen this before when you did Fourier series. Okay. So what was Fourier series? Fourier series was basically saying that, look, if you have any function that has some periodic property in 0 to 2 pi, then I know two functions that have these periodic property. Those functions are cosine and sine. Okay, and then you said, aha, so I'm going to use these cosines and sines as basis functions. And then you say that, oh, well, you can give me any function that you want, but I'm not going to look at it because I can always write your function as a linear combination of my functions. Cosine 2 pi nx plus bn sine 2 pi nx or pi nx, one of those two. Okay, if you since I'm including only integers, maybe I can just write pi nx, or equivalently, instead of cosine and sine, I can also use the exponential notation. Okay, so what are these ans and bns? Well, there is a way for you to determine what the ans and bns are, right? The Fourier coefficients. You use the property that cosine and sine, just like I and j, are orthogonal functions. Just like I dot j equal to 0, there is, if you multiply cosine and sine and integrate over an entire interval, you find that that is equal to 0. But if you integrate cosine and cosine, that is not 0. And if you integrate sine and sine, that is not 0 over an entire interval, right? So use this orthogonal property, just like I dot j equal to 0, to figure out these Fourier coefficients. So there is a way for you to determine the Fourier coefficients. That is exactly what the statement above is. When I say y of x is c1 y1 plus c2 y2, and I claim that every solution can be obtained from these y1 and y2, all I mean is that there is always a way for me to figure out what c1 and c2 are. Just like in a Fourier series, you always have a way of figuring out what an and bn are. Okay, so all of these mathematically have the same property. Okay, I think we will talk a little bit about Fourier transforms later, but I'm not sure we'll talk about Fourier series in this course. Are there any questions about any of this? Any questions or any comments? Okay. So again, as I've told you, we have managed to say an awful lot without actually solving a lot of equations. We will remedy that in the next week as we talk more about these equations. But now let us change gears slightly and talk about inhomogeneous equations. That is where we started, right? So why should we worry about inhomogeneous equations? So remember how we motivated homogeneous equations using the mass spring example, right? So I can actually use the same example to motivate inhomogeneous equations also. So let us say that you have, instead of a mass spring, you can think of a simple pendulum because they obey the exact same equation, a bob strung on a wire, and then you let it go. And for small theta, this follows a simple harmonic equation, right? So you can figure out the solutions and all those things. Now, suppose if I put in some air drag, right? So there is friction, and then that is slowing the bob down, then I will have a term that is linearly proportional, so that is proportional to velocity. So I wrote an equation like this: my double dash plus cy dash plus ky equal to 0, right? So if there's no friction, of course, the cy prime term doesn't is not there, and the rest is just Hooke's law applied to Newton's law for a Hooke's law of force. Now, let's actually make this slightly more interesting by claiming that this mass is actually charged. So there is some charge Q, okay, and I'm putting this in an electric field that is oscillating. So I'm putting it in some kind of an electric field, and the electric field is some E0 cosine omega t or whatever it is that you found in the last semester. Then, of course, this bob is going to be either pulled in the direction of the electric field or away from the direction of the electric field. Whatever it is, the electric field is also going to play a part in the motion of this guy. Okay, which means now in addition to the simple harmonic motion, in addition to the damping force, there is also a driving force, a driven oscillator. Okay, and this driven oscillator would have the equation my double driven, the driving force is also a force. I should club it as part of the force, and this force would be some function of x. Okay, sorry, some function of so rather in this example t, because I used an oscillator example, so this is some function of t. Okay, now this is admittedly a harder problem to solve than before because I have a non-zero right-hand side, and this makes this equation inhomogeneous. Okay, so these are practical examples which necessitates the study of inhomogeneous second order ordinary differential equation, the general form of which is y double prime plus p of x y prime plus q of x times y equals some function on the right-hand side. So notice that now if I have two solutions, y1 and y2 of this guy, a general linear combination of those two is not a solution, unlike the homogeneous part, which you can quickly verify yourself. Okay, so the question is, what is a general solution for this equation, and how do I understand this? So what is the terminology? So the terminology is as follows. The general solution. So let me also write, so let's call this A, and let us write down the corresponding homogeneous equation for this guy with the exact same coefficients P of x and Q of x. But I will put the right hand side to be equal to 0. Okay. So if I'm doing an experiment in a lab, right, and I'm supplying the force that is causing the bob to move, then I can investigate the same physical system, putting in the external force or switching off the external force. That is the difference between the inhomogeneous part A and a homogeneous equation B. Okay, so let us look at both these equations. The general solution of the inhomogeneous equation A of the inhomogeneous equation. I don't want to write it, so I'll just write general solution of A. Okay. Now this can be written, it turns out, as a linear combination of two guys. So y of x, which is a general solution of A, can be written as yh of x plus yp of x. And I should tell you what yh and yp are. So assuming again that there is some interval I where all these functions don't blow up in your face, everything is continuous and well behaved, I can always write this down. YH is the solution of the corresponding homogeneous differential equation. So YH is a solution of B. This is a solution of B. Okay. And this is a solution of A. And now you wonder, wait a second, y of x is a solution of A. So you're writing a solution of A in terms of the solution of A. That doesn't make any sense. But there is a slight difference. You know that a second order differential equation has two constants. So it turns out that in the general solution of A, I can always dump these two constants in YH, because YH, as you know by now, since this is a homogeneous differential equation, I can always write this as C1y1 plus C2y2. Okay, where C1 and C2 are some constants and Y1 and Y2 are two linearly independent solutions of B, the homogeneous equation, which means I've exhausted both my constants. So this Yp of x is basically a solution of A that has no undetermined constants. So this has no undetermined arbitrary integration constants. Arbitrary constants. So it turns out that I can write a general solution of A in this particular form. Of course, this is easier said than done. I'll have to tell you how to find Yp of x, which is what we will do starting next lecture. So assuming that you know how to solve the corresponding homogeneous equation, you can write down the general solution of the inhomogeneous equation as a linear combination of the homogeneous part and a Yp of x, which is a solution of the inhomogeneous equation but doesn't have any constants in it. Okay, so this is the definition of the general solution of A. Okay, so now what is a particular solution? Just like in the case of homogeneous equation, suppose you fix C1, C2 to some particular values. This gives you a particular solution of A. Okay. So just like in the case of homogeneous equation, suppose if you're solving an initial value problem or whatever it is, and you have a way of figuring out C1 and C2, plug in those C1s and C2s in this equation. And for that specific value of C1 and that specific value of C2, you have a specific solution, and that specific solution is called a particular solution, just like before. So the general solution is a linear combination of the homogeneous part and a Yp, which is a solution of the inhomogeneous equation without any constants. So let us actually show that this makes sense. Okay, I will not show that this is the general solution in a general fashion, but I will motivate that this makes sense. And I will use the notion of operators here, even though I'm technically not supposed to, but it's okay. So let us rewrite this differential equation, A and B, in this form. So I will call L as the operator d square over dx square plus p of x d dy plus q of x. Okay. Suppose if I call this L. So I'm sure you guys went through quantum mechanics, and hopefully you put a hat on all the operators. Of course, in this course, we may not have to worry about such niceties. So we can simply either call it L or L hat, but since I'm a physicist and I'm used to this notation, I'll call this L hat. If it confuses you, don't worry about it. So then I can rewrite A and B as follows. The inhomogeneous equation is the linear operator acting on Y to give me R of X. Okay, so this is basically my A, and the inhomogeneous equation is linear operator acting on Y giving me 0. All right. So suppose if I have a solution for the homogeneous equation, and suppose if I have a solution for the inhomogeneous equation. The question is, if I add these two guys up, does it still become a solution of the inhomogeneous equation? Let us use this particular notation. Let YH be a solution of the homogeneous equation, by which I mean that L acting on YH is 0, and let somebody's saying, shouldn't the term with P of X be ddx and not ddy? Oh, yes, absolutely. Thank you very much. Thank you. Yeah, this is ddx. Yes, sorry, that was a typo. And let YP be a solution of the inhomogeneous equation. If I say YP is a solution of the inhomogeneous equation, I mean that L acting on YP will give me R of X. So the question is, what happens if I add YH and YP? So L acting on YH plus YP. The question is, does it still satisfy the differential equation? Well, the inhomogeneous differential equation. Well, the point is that this is a linear operator. So this basically has a bunch of derivatives, right? So suppose if I want to ask what happens if I act L on Y1 plus Y2, then I can act all these guys, d squared dx squared plus p of x ddx plus q of x first on Y1, and then I can add this on Y2 later and add them up, right? So that is what is meant by a linear operator. So if I want to ask what does the operator do to the combination YH and YP, I can as well write this as L acting on YH plus L acting on YP. But since YH solves the homogeneous differential equation, the first term is 0. And since YP solves the inhomogeneous equation, the second term is R of X. So which means if I take a combination of these two solutions, this gives me R of X, which is the defining criterion for the solution of the inhomogeneous equation. So at least we know by inspection that this linear combination still solves A. Okay. Does this make sense, or should I go a little slower? The condition that something solves A is that if I take this linear operator A and act it on that solution, it should give me R of X. And I have basically verified that criterion. I took L and acted it on YH plus YP and I got R of X. So I can always claim that this particular way of writing things, decomposing things, is a solution of A as written. Okay, so that is the first one. There's something also interesting happens. Suppose if you have two solutions of A. Okay, so let us say that let Y1 and Y2 be two solutions of A. Okay. Now, what happens if I act on the linear operator on Y1 minus Y2? Okay. So in other words, what I mean is that L acting on Y1 is R of X and L acting on, Y2 is R of X. Now I can ask myself what happens when I act L on Y1 minus Y2. And this obviously is L acting on Y1 minus L acting on Y2, which is R of X minus R of X, which is 0. So which means if I have two solutions of the inhomogeneous differential equation, I can take the difference of these two solutions and that will be a solution of the corresponding homogeneous differential equation. This means that y1 minus y2 is a solution of the corresponding. So corresponding is important because I'm looking at the exact same equations, the exact same p of x and q of x. Corresponding homogeneous differential equation. Okay. Now with these two statements, it turns out that they can actually show that any general solution of the inhomogeneous equation contains all possible solutions. So this is also given as a theorem in your book. Exactly like a homogeneous differential equation, the general solution of A contains all possible solutions. In this case, what does it mean? Remember that in the case of homogeneous differential equation, it meant that I can always write any function that is told to me as a solution of the homogeneous equation as some constant times the first basis function plus some other constant times the second basis function. In this case, what it means is that if somebody gives me some y of x, so if y of x is a solution of A, okay, somebody claims that this y of x is a solution of A, then this means that y of x can be written as some particular c1 y1 plus some particular c2 y2 plus yp. That is, there exist some values of c1, c2 such that y of x can always be written in this fashion. Okay, so this is the content of the last theorem in the case of inhomogeneous equation in your book. Just like in the case of homogeneous equations, in this case, remember that both the constants are dumped along with the solution of the homogeneous part. And now I have a particular, now I have a yp that I should figure out somehow. Okay, so I'll tell you how to figure out yp the next lectures. But the statement that the general solution contains all possible solutions in this case means, analogous to the previous case, that any given solution, if somebody finds another solution y of x, then you can always find some values of the constants c1 and c2 such that y1 can be written as some particular value of c1 times y1 plus some particular value of c2 times y2 plus yp. Okay. In other words, there is nothing special about y of x. You can always express y of x as a linear combination of yh and yp with some specific constants. Okay. So we'll stop here for today, and then we will take this up next lecture where we will discuss how to figure out yp.
Sir.
Hello, sir.